Okay, chemists, we've learned a lot of reactions related to alkenes and alkynes, and the purpose of this video is to do a bunch of practice. We're going to start off with reaction practice, predicting the products of reactions that apply the new ones we've learned to just different types of alkene and alkyne starting materials. So for each of these, I'm going to remind us just what the transformation looks like and figure out what the product is. This is a hydroboration reaction, so this is non-Markovnikov addition of H and OH. We keep all our carbons, so I have a 5-membered ring. I lose the pi bond. Non-Markovnikov, meaning H on the more substituted and OH on the less substituted. So I get OH on that carbon, and then H on the other one. This occurs with syn stereochemistry, but I can't tell in this example because we didn't generate any asymmetric carbons. Done. Right next to it, B. This is halogenation. The pi bond will become a 1,2 dichloride, and you get anti-addition. If there is an outcome that's relevant, point it out in words. Why did I arbitrarily make this chloride away from you and this one toward you? Because it was arbitrary. You will get the enantiomer. So it's a good idea just to pay attention to stereochemistry and the mixtures that you might get. On to C. This is addition of HBr. This is a Markovnikov reaction, so I'm going to get H on the less substituted and a bromine on the more substituted carbon. So we get a bromine there. This is achiral, no stereochemistry to worry about. Next, another HBr addition. Interestingly, this is also going to go Markovnikov. We get H on the less substituted, bromine on the more substituted. That is a good cation, actually, because of the resonance intermediate. This one I'm going to show the mechanism of just to remind us how it works. The pi bond attacks the H, the bromine leaves, you get a more substituted cation, but also a better cation because of the chlorines lone pairs, which can donate through resonance. That's really why you get this particular intermediate. You get a chloronium ion intermediate. And then bromide sees that, and it attacks that and sends those pi electrons right back up where they were. So you get what's called a geminal dihalide. Gemini meaning twins on the same carbon. So this is a geminal dihalide. Moving on to E. This is halohydrin formation, bromine and water. You're going to get a bromine on one carbon and an OH on the other. It's similar to the mechanism for bromination, so you get anti-addition with one bromine and one OH, and you'll get the racemic mix because that's chiral. Right next to it, part F, this is hydrogenation. Hydrogenation occurs with syn stereochemistry. There's this methyl drawn into the page on the other side there. So I'm going to get two hydrogens attacking from the front of your screen or from the back. If they attack from the front, that will actually push the methyl away from you. What would it look like if they attacked from the back? Well, that would push that carbon group toward me. And both of those are correct. Now I can't get away with drawing just one of these and writing the racemic symbol because this is not a chiral molecule. It doesn't have an enantiomer. This is a unique example where I get a mixture of diastereomers because we've desymmetrized the molecule by doing that hydrogenation reaction. Moving on, ozonolysis, one of our more recent ones. Ozone cuts the carbon-carbon bond where there's an alkene, so it opens up this 6-membered ring. Every carbon that used to have a double bond is now doubly bonded to an oxygen, so I get a ketone and an aldehyde. You could stretch that out if you wanted to and draw it a little bit lengthier. This is a 7-carbon chain, 2, 3, 4, 5, 6, 7, with a ketone on one carbon and an aldehyde on the other. Another ozonolysis right next to it. Cut that carbon-carbon bond, you get two separate molecules. One cyclopentanone, the other one acetaldehyde. Just drawing it upside down to show you where it came from. Still going, another ozonolysis. Wow, ozone is one of those gaseous reactions that's hard to stop. As long as every alkene is fairly electron rich enough to do the reaction, you will cleave all of them, in this case all three, and I'll draw them as if they're lined up in the same way they were when they were in the molecule. So the top half becomes that 3-carbon chain, and then I have one more lengthy carbon chain like so. If you look, I actually have 2 of the same thing. So it's not out of the question. You can see this somewhere where they draw it a little bit differently, and you have to realize that this means the same thing as simply drawing this dialdehyde like so, and then another dialdehyde with one more carbon in between. There happen to be twice as many of that 3-carbon aldehyde as the 4-carbon aldehyde. Okay, now it's getting tougher with these pre-existing stereocenters. HBr is going to add Markovnikov to this alkene. We're going to get H on the less substituted and bromine on the more substituted. So first let me just constitutionally draw what we get. Lose the pi bond. I have a methyl in the upper right. I still have my methyl in the lower right, and I have a new bromine on that tertiary carbon. Is it toward me? Is it away from me? It's likely both. So I'll start with filling this in and making it toward me, and then I'm going to draw what it might look like if it's going into the page instead. Ask myself, is that different? Yes, that's different, and it's not the enantiomer, it's diastereomer. The only way to represent diastereomers is to simply draw them both. For now, that's what we'll do. We don't have the little plus-minus symbol like we do for a racemic mixture. Okay, this is hydroboration. This is the same as the reaction we did all the way in the beginning, but a much more complicated example. It's going to be non-Markovnikov, and we're going to get syn addition of the H and the OH across that alkene. So let's redraw it first without the pi bond. There's this pre-existing stereocenter along for the ride in the lower right. I have a methyl along for the ride as well. Where's my new H and my new OH? This is non-Markovnikov, so that means that the new H is on the more substituted carbon, and the new OH is on the less substituted carbon. We actually just created 2 asymmetric carbons, and relative to the pre-existing one, they could be toward you or away from you. So I'm going to draw another possible product where I change the direction of that new H now coming out of the page, and that new OH also coming out of the page. Once again, a pair of diastereomers. A hydrogenation on an alkene occurs with syn stereochemistry. There's a pre-existing ethyl up at the top. I always draw the stuff in that doesn't change first. Draw everything the same first, and then change what's changed. Now we have 2 new H's, and they could be going into the page, or they could be coming out of the page. So I'll consider them both. That's because hydrogenation occurs with syn stereochemistry. And then I'll look at that and I'll ask myself, did I accidentally specify any direction where there isn't any? And yes, I think I did. It's this position here. That's not an asymmetric carbon, so it's kind of pointless to show the hydrogen with any direction. But it's not pointless to show the direction of this hydrogen. That is an asymmetric carbon. So either specify the direction of the methyl, or specify the direction of the hydrogen, or you can specify both. That's okay, as long as it communicates the same information. Once again, we have a pair of diastereomers. I cannot write the little racemic symbol. Now we get to less stereochemistry, some alkyne reactions. Hydroboration will first turn that terminal alkyne into an enol with the less substituted carbon getting the OH. But remember, enols don't stick around. They tautomerize, and you'll get a 3-carbon aldehyde, propanal in this case. Right next to it, this is oxymercuration of the same alkene we have all the way up in A, I believe. So this is the counterpart to A. This is the Markovnikov version of that reaction. You get an OH on the more substituted carbon and an H on the less. That's a stereocenter right there, so I'm just going to draw plus minus with only one stereocenter. I don't even bother specifying it. Communicate that you get both enantiomers with that symbol. O is a dissolved metal reduction of an internal alkyne. This will give you the trans alkene. Check your carbon count. 1, 2, 3, 4, 5, and 6. So I need a 6-carbon chain, 2, 4, 6, with an alkene right in the middle, and it's got to be trans. So I will write that, trans alkene. Or alternatively, you could say E, number 4, with Geigen, opposite. Right next to it, the counterpart. This is the cis reduction of this. Looks like it's an extra carbon. So we have 7 carbons, and it's got to be cis. 2, 4, alkene, and then that ethyl is a cis alkene. Okay, lastly, let's take a look at some forward syntheses and see if we can figure out what the products are as we start to gear up towards actually doing synthesis problems. So, in 42A, this is our brand new reaction of making an internal alkyne. Remember, this is soda mid, which forces your alkyne to become an alkyne anion. And then what is NBU? That's just normal butyl. So this is bromobutane, great SN2 acceptor. So you can imagine that anion hitting the carbon attached to the bromine leaving. You take your alkyne and you attach 4 carbons. 1, 2, 3, 4. Then we do a Lindlar reduction. Lindlar does a cis reduction, but more importantly, it stops at the alkene. So I take my 6-carbon alkyne and it will become a 6-carbon alkene. In fact, that's one of the main reasons we use the Lindlar reduction, and quite frankly, more often the dissolved metal reduction, to do what's called a partial reduction of the alkyne. If you didn't have that, if you just use H2 with PD, you would go with just the single bond. You would get an alkane. Lastly, in this scheme, we're going to do a hydroboration. That's going to put an OH on the less substituted carbon and an H on the more substituted carbon. We're not even creating any stereocenters here, so we can just draw it. So I get a 6-carbon primary alcohol in the end. Okay, right below it, another alkyne anion gets formed. This time we do an SN2 with bromoethane. You do not need to draw curved arrows for this. This is a reaction problem or a synthesis problem where you actually don't want to draw curved arrows too much because it makes it look accidentally like a mechanism problem. This is not a mechanism problem. I'm just showing it here to help figure out what the products are. So I have my alkyne from the beginning, and then I added 2 extra carbons. And then it looks like we're doing another deprotonation. So I'm putting another anion on the other side of this, and it will do another SN2, this time only adding 1 carbon. So I get an internal alkyne, total of 5 carbons. Lastly, they want me to do, or almost last, they want me to fill in the reagents. So what reagents do I use to turn it into the trans-alkene? This is going to be a dissolved metal reduction. So sodium and ammonia gets us to the trans-alkene, and then MCPBA will give us an epoxide. And you could simply just draw it like that. That's sufficient. If you want to be a little fancier, you could specify that there is syn addition of the epoxide. I could, let's say, show the syn relationship between that methyl and that H, and likewise the syn relationship between the ethyl on the other side and the hydrogen. And that actually has an enantiomer, so I could get really fancy and show that you make a racemic mix of this. That means when you're doing a synthesis problem and you want to make an epoxide with specific stereochemistry, you go backwards and figure out what the alkene was that you started with.